let's get started. So we ended last class period. I quickly flipped to this slide because I talked about the stuff up to this slide as we were going through. Now what this slide is showing us the top level of the earth. So the topmost level of the earth is the crust. Notice we have two different types of crust, the continental crust and the oceanic crust. And it's very easy to tell the difference because the oceanic crust is much thinner than the continental crust. The oceanic crust is somewhere like, 10 kilometers thick, whereas the continental crust is somewhere between 20 and 60 kilometers deep. Why would those two be different thicknesses?
The amount of pressure that they were saying? Or no?
Kind of in the ballpark. It has to do with the density. The earth is behaving kind of like it's a fluid. And so things will float up and things will float down. And so the crust is floating on the mantle, but we have different densities for the two materials. The stuff that makes the continental crust is lower density material. And so it would tend to float higher and actually is thicker so that you have the same weight going across here as you have over here, right? But because of different densities, it's a lot more space. One of the things that's really surprising is if you have something that's really heavy, like let's say a glacier on top of the land, after the glacier melts, the land will rise underneath it because it was lower, having the glacier pushing down on it. You take away the weight of the glacier and it actually springs back up. Not springs up like, oh, look at it move, but springs up as in over the course of years it rises back up. So you have the lower density continental crust and the higher density oceanic crust. And then, of course, you have water on top of the oceanic crust that's helping to give it more load as well. So this brings up a Greek word, isostasy. Iso means the same. Stasy is standing. So isostasy equals standing. That's a term that tells us about the floating and them, being in their different levels because they're actually floating on the same type of material. So they have to adjust their heights to float. Okay. I've already answered that. I'm going to skip that because we're not using the clickers today. And come on to continental drift and Alfred Wegener. So Wegener said that we should have these pieces, these plates floating against each other, right? The cracked up plates I talked about. And so that thing we tend to call continental drift, wait, it says it right there. I don't need to write it. Continental drift, or as a science, it's plate tectonics. Tectonic plates are the names for the different pieces. Think of it like an egg. You crack the egg, you have eggshell that's broken up into different plates, and then those plates will slide around floating over the asthenosphere. And so Wegener proposed that at some time in the past there had been an island of Pangaea. And so here is a drawing of course, we have some parts missing there, of continental masses brought together. You see Europe here. What's missing from Europe? Asia should be connected there, right? And so that's what Pangaea is. Now, geologists and physicists, got a question, Brandon?
So I was looking at a picture of all the plates or whatever, and do the actual continents move or the plates? It's how do the plates move? They're
the continents are on plates,
right?
And with I think only one exception, a continent is completely on a plate, and so as the plate moves, the continent just floats with it. It's kind of like if if you're on a cruise ship, do that this summer, your cabin just moves wherever the boat does.
Right.
That is the same idea. The continents are on top of a plate, and so they move wherever the plate does. Okay, now let's see. What was I saying? Anybody want to bring back my train of thought? Yes, scientists and geologists, physicists and geologists, have worked very carefully to try to match the positions of these plates as a function of time. Now, I know I have a slide that has the information we need for that. So when we get to that slide, then I will talk about how they can tell us about how these plates have moved over time. So sad. How was Wegener's idea treated? Dismissed. They totally dissed his idea, because that's what it means, dismiss him. So they totally dismissed his idea, saying, you have no reason for this. You just looked at a map and saw that the shapes fit and made this crazy idea. Any more luck?
We'll see.
Okay, so what was needed was more information about the motion and what the seafloor looks like. Mapping the seafloor shows some funny things. Where is the ocean the deepest? At the edges. At the edges, you have huge mountain ranges, you have deep trenches. In the middle, you have the mountain ranges. And so the deep trenches are at the edges, so you might have heard of what's the name of the trench, right?
Mariana Trench?
Yes, Mariana Trench, the deepest part of the ocean. It's a really deep trench. But then you have these mountains in the ocean. So if you look at the ocean floor, generally your deepest points are here, where the continental plate meets the oceanic plate, and then it's shallower in between. And notice it goes up here. Now, this picture here actually corresponds to what we're going to be doing in lab today. Kind of. What you see there is a cross-section of the ocean floor. And if you look at the ocean floor, the first thing to note is that this has arrows showing motion. We have hot material that's coming up. And that hot material coming up causes what we call convective cycles. Hot material floats up, cools, goes back down. And so you see those two circles, one counterclockwise and one clockwise. Those are convective cycles caused by this hot material flowing up in the center. But of course, those convective cycles are then going to start pushing those plates apart. The hot material coming up the center softens the rock where it's coming up, and so the rock at the center where it's coming up gets soft, and you have the convection pushing the plates apart, and what happens is what we call a rift forms. They get pushed apart. So the ocean plates are getting pushed apart by these rift zones. Of course, when you push them apart and you have hot material coming up, what's naturally going to happen? Hot material's coming up, you push them apart, what's going to happen? Say it louder. What do you say? Okay, push it apart, but what happens in the center then? The hot material comes up and keeps water. Well, what's water going to do when it meets that hot molten rock? It's going to cool it down, and that molten rock is going to cool it down. It becomes a solid. It's going to be too fast for it. So it's going to become a solid, so it's going to create more ocean floor. So this process spreads apart the ocean floor and creates new ocean floor. How do we know this? Well, one thing that we can do is we can go and we can check and see, yes, we have these mid-oceanic rifts, these zones in the ocean that are basically cracks that have lots of little volcanic activity, volcanic vents, where material is coming up. There's another way, but like I said, that's coming up in the later picture. But let's look at the edges now. I've been focusing on the center. So you're going to have some volcanism. Yeah, I'm really zoomed in. Now you can hear me. You're going to have some volcanoes here at the rift zone. Back when I was in college, I read the Rift War Saga. And every time I use rift zone, I think of that. But now let's go to the edge. So here we are at the edge. This here is continental plate. This here is, of course, oceanic. And what I say about the relative densities of the two? How's the density of the continent compared to the density of the ocean floor?
Ocean is more.
The ocean is more dense. So when those come together, they can't just go crunch and still have motion. One of them slides underneath the other. That process we call subduction. Sub because it's going under. So this region right here is called the subduction zone. Because the oceanic plate is subducting, sliding underneath the continental plate. But you know that if you rub your hands together, they get warm. Well, this is rock rubbing against rock. It gets really warm. Warm enough that it melts rock. So you melt rock right there, but the molten rock is less dense than the solid rock. So the molten rock floats up to the surface, and when it gets to the surface, what does it make? What do we call this thing? Volcano. So we have volcanoes that are at the mid-ocean rifts, as well as the boundaries between the oceanic plates and the continental plates. So how many people know what the Ring of Fire is? Yes. How many people can sing with me? And it burns, 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 that ring of fire, that ring of fire. Okay.
Isn't it the volcanoes that are all around that place?
Yes, it is. I swear I have a picture. That's the one I've been looking for. I'm just going to go to this picture here of the plates. Here are our major plates. There are, 8 major plates? And the Ring of Fire is, I should use red because it burns. And actually comes down with the Nazca plate. You're going to have some little action there, but that's basically the Ring of Fire. It's the boundary of that Pacific Ocean plate. Question?
Okay, I'm sorry. I don't know if I'm missing something, but so North America was attached to Africa at some point.
Yes.
But how was the continent connected when the plates are the continent on the plate is so far away? I don't understand how the continents were connected.
Okay.
The plates were that big.
If you look at the picture here, you see that we have the African plate here is brown.
Yeah.
The South American plate here is purple.
Yeah.
And so these arrows are telling us the direction that those plates are moving with respect to each other. So what we have is rifting that's occurring along here. And it's the material that's coming up is pushing those two away from each other.
Okay.
And so that's how we now have the separation between them because of that rifting that's been going on. And it's been creating the ocean floor here that wasn't there when they were connected.
Okay.
Now, how do we know that is another question, right? We can see that there's that shape, but to know that, we have to look at, this is just describing, actually this is starting it right here. We studied magnetism in the ocean floors. It was discovered by sailors that when they're sailing across the ocean, sometimes their compasses started being wonky. They wouldn't point in the right direction. And so as you know, the scientific method, let's practice once again. What's the scientific method? It starts with observe something interesting. So they observed something interesting that the compasses aren't working right when you go across the ocean. And so then what's the next step?
Why is there compasses
You create a hypothesis that does three things. What are those three things? It's based on scientific ideas, makes testable predictions, and explains why the observation occurred. So scientists come out and they say, well, what could cause that? Maybe there's a local magnetic field that's interfering with the magnets. Right? They know scientific idea, a local magnetic field is going to interfere with magnets. It would be testable because then you could come in and you could try to test what the magnetic field is and see if you have something that's changing directions. And so what did they find out? Yes, they have magnetic fields that are changing. And so this picture is showing what they see when they read the ocean floor. They read the ocean floor just like your computer reads its hard drive. The computer's hard drive has a gel in it with magnetic material. And you put a strong magnetic field in that gel, the magnetic material will align in the gel. And then they come by and they check what direction it's aligned, and that's how they read it. So they do that on the ocean floor, and they find that these regions here are normal. That is, if north was in this direction, you'd have your compasses point like this. But in the brown direction, the compasses are pointing the opposite direction. So the magnetic field is reversed back and forth. And one thing you notice in these pictures is it's symmetrical across the rift. It's the same on one side as it is on the other, right? So you can read from center to the right or center to the left and you get the same pattern. That's actually important because what should be happening in a rift zone?
Volcanoes.
You what?
Volcanoes.
Okay, you have volcanoes, you have magma coming up, you're pushing the plates apart, and new ocean floor is forming from that magma that came up. And so you create an ocean floor on both sides of the rift zones at the same time, and the Earth's magnetic field is what's causing the alignment of the magnetic material of the ocean floor. And so both sides will have the magnetic fields aligned. Those get pushed out, new material comes up. If the Earth's magnetic field changes, so do they. And so that's how we have the ocean floor with these reversing magnetic field directions. And so we can use that to read the ocean floor and say the Earth's magnetic field has switched back and forth through history. Now, using radiometric dating, they calculate that it's been about every 200,000 years the Earth's magnetic fields switch. So what was the north magnetic field becomes south and vice versa. It's been about 1 million years since it last happened. So we're way overdue. But the process doesn't occur overnight. So it's not like you're going to be in one of the movies where you wake up and there's no magnetic field and the birds are flying into windows, which also wouldn't happen. But the Earth's magnetic field must switch. We have other things we can observe that have magnetic fields. Primary among them, the sun. The sun has a magnetic field, and we found that the sun's magnetic field switches poles about once every 11 years or so. And so the sun switches a lot more often than we do and a lot more repeatably. And so by studying the sun, it helps us understand more about what's going on with the Earth. So Earth's magnetic field switches back and forth, and we can read the times by looking at the ocean. So now we have 8 large plates and some smaller ones. So coming back to this picture, we talked about this Pacific plate with its ring of fire. What's going on at each one of these places, you can see by the arrows what's going on. So here, where we roughly are, okay, I say where we roughly are, I'm from California. Sorry, I by default go to California. We are out here. What's going on there? Nothing. We're in the middle of a plate. We shouldn't have much earthquakes because we're in the middle of a plate. Faults are places where you have a crack in your plate. And those cracks are generally formed near the plate boundaries where you have a lot of stress because of relative motion. So out here, they say that we are on the Mid-America Craton is the name for it, a region that really doesn't have many faults. Now, there are faults. You know that the biggest earthquake in the contiguous United States was in Real Madrid, was it Missouri? Something like that. The Real Madrid earthquake made the Mississippi flow backward for 3 days. Pretty impressive. So we're out here. If we look at California, what do you know about California and earthquakes? There are some. There are a lot. What do people say about California and the big one? Well, the 1905, 1906 earthquake was in San Francisco, but the big one that's coming that hasn't happened yet. What's going to happen?
Oh, the San Andreas. Yeah.
Okay, the San Andreas Fault.
Is this the one that's supposedly supposed to make us go underwater?
Yeah, they say that California is going to fall into the ocean. Well, news break.
Let's stay out here then.
If you look at this picture, we have California, which is right here. Well, I went too high with California, but that's because I love my Golden State.
Was the entire California supposed to be submerged? Yes.
Well, only for people who don't know what they're talking about. Okay, so if we look at this right here where California is, what direction is the oceanic, the Pacific plate moving with respect to California? Has arrows to tell you. Well, the one that's on the yellow is going to be the direction the oceanic plate's moving with respect to California. So what direction is that? Okay. So the oceanic plate's moving like that. California is moving like this with respect to it. So we have what we call a strike slip. Strike slip is when they're going sideways between the two. What's going to happen for California to, quote, fall into the ocean is that the separation between this boundary gets moved a little. That is, material that is on one gets moved to the other. And there was some speculation that back the day my sister got married, they had the Landers Tumbler. It was a really big earthquake. It was like 7.2, I think, moment magnitude. And there was some consideration that the plate boundary at that point switched from here to like that, which would mean that California fell into the ocean that day. Was California underwater? No. If it fell into the ocean, it would just be, it's now part of the Pacific plate instead of part of the continental plate. So when people talk about California falling into the ocean, they're not talking about it falling down into the water. They're talking about switching over from being part of the continent to being part of the ocean, which is interesting. Now, if we look here, we have this sliding, and because of the sliding, it's creating stress. So we have all of these faults in California that are just little cracks. And because of all that sliding, some of those cracks get stressed, they get widened, and eventually there's enough stress that they slip against each other, and that's what happens that's what causes an earthquake. When you had two pieces of ground that were being pushed in opposite directions, slide against each other, you have an earthquake. And so the earth actually does move. You feel the earth shake under your feet. If we look at the other major plates, we have the Eurasian plate. Here we have the Indian plate. Based on the readings of the ocean floors, you can find animations showing how the continental masses have moved over time. And you'll find that Pangea isn't the only, they're all together shape that they have put together in this. You also have things like Laurasian Gondwana land. So you watch those animations, and what I love to see is to watch the Indian plate. You've heard people talk about India as the subcontinent of India. If you watch those animations, it becomes clear why. You have all of these plates moving around like this, and then all of a sudden you have India, which is down by Australia, just comes shooting up and slamming into Asia, and crunching together to where they're stuck together. You can see that it's still, based on those arrows, what are the two continents doing with respect to each other?
moving into each other.
They're moving into each other. Well, if they're moving into each other, you're probably going to have some subduction there. It also builds mountains, because just like if you have two cars hit each other, you have them crumple. The crumpling builds mountains. So we have the Himalayas that are created, and it was actually very funny. We were on a geology trip, and the leader said something about the Himalayas, and somebody said Himalayas. He said, well, I'm going to pronounce it the way they pronounce it in the Himalayas. So apparently that's the correct pronunciation, and that's what I continue to call it. So, okay, Larissa, your sister lived close to there. Do you have valuable input on this? Because you might.
I never heard you say Himalayas. But maybe
I know. I'm trusting Ben Clausen on this, that because he's been there for geology purposes. And
yeah, I've been
okay, so the plates. How do we know about the motion? How do we know? It's not because Wegener said that it looks like they should fit together. How do we know? No, we do. We have good data to tell us that they've moved. What's the data that tells us that these have moved around?
Is it the vegetation?
Not the vegetation, although there might be some data in there. It's just not what I've been talking about. Do you have an answer, Brittany? What about them? What do we have to tell us about the motion of the plates historically?
The seafloor.
The magnetic fields that are frozen into the seafloors. That's what tells us about the positions and the motion. So it's, the ideas of the large motion and having a Pangaea and a Laurasia and a Gondwanaland, those are not just fanciful. They're based on actual data. Okay, motion. Earth plates move in different directions at different speeds. Continental plates move slowly. Oceanic plates move faster. Let's go back to this picture. I spent a summer acting up in Skagway, Alaska. And so Skagway, Alaska, I think is somewhere, it's somewhere in that ballpark, I think. And so you guys know about Skagway, right? What's it famous for? Alex?
I have no clue what that is.
North to Alaska. They had a gold rush in Alaska. And Skagway is a gold rush city there in Alaska. And what was special about Skagway is that it had a deep water harbor. And so ships could come in to Skagway. Actually, it's not where the gold rush started. It started just a little bit north of Skagway in Dyea. So Skagway is, I can't tell here where exactly it is, but let's say that Skagway's here, Dyea's there. And Dyea had a shallow water. That is, boats couldn't come into shore because it had a slow slope. Where Skagway went, and boats could come into shore. But to get to the gold fields in the Yukon, you had to, you want to go the shortest route. And so ships would come to Dyea, and they would come at high tide. They'd put out a boardwalk, and people would have to get all their stuff off and get out of there before the tide went down. So when I was up there in Alaska, I went on the ranger tour of Dyea, and it was one of the coolest things. Our ranger was totally into geology, and he had his little visual aids, his hand-drawn charts and stuff. And one of the things that was really amazing to me was how quickly the land level was changing in Dyea. I think he said it was something around a foot a year or something that the land level was rising, or maybe it was an inch a year. Sounds more reasonable, inch a year. That land level was rising. And so since the gold rush, land level was like 8 feet higher than it had been during the gold rush. Why would the land level be rising there at Dai?
Plates were going into each other.
Okay, yeah, things are pushing into each other. So we have an oceanic plate that's subducting under the continental plate, and as it subducts under, it's pushing up and wedging up the continental plate, making the land level rise. Now, another thing you see there, see where my blue mark is just off of that? You see that little black chisel-looking thing? That used to be a rise in the ocean floor. But as the ocean floor got pushed underneath the North American plate, these little rises are kind of like pancakes. They're getting scraped off by a spatula. And they're getting deformed by that motion. So this was probably roughly circular, but as it got scraped off, it got flattened to make a flat island there. Nobody here seems nearly as interested in this as I am. I just thought that was the coolest thing in the world. Okay. Yeah.
No, it's not absorbing it. It's like the food coloring is moving just fine. It's not absorbing it. Even when I directly put it on, it would just kind of wash off.
Okay. Next step then, theft. You know where the janitor's closet is?
No, I think
Next to girls' dorm.
Okay.
Or not girls' dorm.
Yeah,
Girls' bathroom.
there we go.
Yeah. Go in there and see if you can find any sponges. Girls' dorm. What would I know? It's over there. Okay, so let's continue on with this. We have 3 types of boundaries between the plates. Divergent. Where do we find divergent boundaries? Divergent means they're moving apart. Where do we find boundaries moving apart? Where do we find them moving apart?
On the seafloor.
Where we have these rift zones. Right, there's where we have commonly divergent boundaries. They're moving apart, so you have a rift forming with magma coming up to make a new ocean floor. Convergent boundaries, those are usually going to be where you have 2 plates coming together, a continental and an oceanic. Transform is actually the name for the type of fault that causes strike slip. So California and the Pacific plate, that's a transform fault because of the direction of the slide. So no magma generation, no formation or destruction of lithosphere, except for when you have earthquakes. So right now we don't have any active volcanoes in California. Yay. They do up in Washington, right? Because you have this Juan de Fuca plate that is, I think it's doing something like that. Okay, moving on then. I've already talked about this feature as we started in the rift zones and the divergent boundaries and rift valleys. There's one rift valley that's above land level that I know of, and that's in Africa, like in Eastern Africa. There's a great rift valley. The rest of them are underwater in oceans. The subduction zones where we have convergent boundaries, we've talked about those. You have deep earthquakes and deformation. And so here we have, well, I've talked about all of this. I can skip over it. One more type of volcano to discuss. Yeah. So here we have talking about the Himalayas. I should have mentioned this here. Here we have a transform fault where we have a rift valley that's been broken up because we have a slide perpendicular to it. So you can have some interesting motion. Any look?
Some towers and sponges.
We're not going to cut the towels. They're probably too big to. How big were they?
Or they were like hand towels. I mean.
So you could fold them over and make them into like 6x6 squares.
Probably.
Let's give it a shot.
I don't know how clean they are. They're in a laundry basket.
Yeah, maybe not.
I can
We'll worry about when I
see.
break. I'm about to break, and then we'll go. Okay. That's a horrible idea. This is a fun lab. It was personally picked by Alex because it's fun. Okay, let's get to shapes of rocks. Because of the when you have two convergent plates, they're coming together, it causes stress, and it will cause what was originally flat ground to start to buckle. How many of you have noticed that when you like drive through a road cut, that's where a highway is cut through part of a mountain, so on the side you see where they had to cut into the rock? You've seen things that are going like this. You have layers that aren't horizontal. One of the fundamental rules for sedimentation is you had transport of material that then fell out of the fluid and settled on land. What orientation is that land? Should be horizontal. So we believe that sedimentation forms horizontal layers. So here you're looking at sedimentation, and it's not horizontal. And some people, of course, say, well, that means that your science is all wrong, and these aren't sedimentary rock at all. That sedimentary rock wasn't the result of sedimentation, it's something else. But geologists say, no, that's just rock that has been deformed because of compression. And so it's, once again, it's crumpling, and they name these crumples. You have the anticline and syncline. Syncline is at the bottom of a valley where it goes up on both sides. I think of syncline, the way I remember it is because sin is down, is bad. And so the syncline is the downside, and the anticline is the upside. I know it's not the best mnemonic, but that's the way I remember it. I looked at their definition was just this. Layers tilt in toward a folded axis or tilt away. And I was like, well, as far as I can tell, that layer tilted in. Right? To me, that tilt in, they seem to tilt in both. So that tilting in and out didn't work for me. But what works for me is the synclines are the troughs, they're the low areas. The anticlines are the peaks, the high areas. When we have a fault where ground can slide against it, we have a couple different geometries we talk about. One of the first things is most faults are not vertical lines. They have some slope to them. And so we call the footwall the one that's underneath. That is, if you were to separate the cut, the one that your feet would be on if you were trying to walk is the footwall. So that's what the picture here is illustrating with the man walking on the footwall. The footwall is the one that is upward facing. The one that's downward facing is the hanging wall. So it has the light here to show that you could hang something from the hanging wall. So when we have a fault, the footwall and the hanging wall are kind of easy to define. Those can be either a thrust fault or a reverse thrust fault. I think instead of a thrust fault, they call it something else. A reverse fault is where you have it go up the slope. A normal fault is where it goes down the slope. So this is showing a thrust fault. You have something that's pushing this so it slides up. And so you can have an earthquake on a thrust fault that is a reverse thrust. The ground goes up on the top. Or you can have it go just the opposite. A normal fault where it just slid down. And then finally, the strike slip faults are where it's sliding side to side. And the San Andreas fault, the big one in California, is strike slip. So every time we have an earthquake on the San Andreas fault, Los Angeles moves north. Los Angeles is on this side of the fault. So when we have an earthquake on that, Los Angeles might move north 10 feet compared to inland United States, which is kind of curious, right? LA is getting closer to San Francisco. You'll know San Francisco, well, at least Oakland, is on the continental side there. And so San Francisco, or LA is getting closer to Oakland. San Francisco, I don't know how well you guys know, but San Francisco's under the red line there. The line is not clear enough for us to distinguish. And if anyone cares, where I grew up is right there, Monterey Bay Academy. The road that comes to Monterey Academy is called San Andreas Road. And so when I learned that was because it's pretty much on the San Andreas Fault, I was like, ooh, that sounds safe.
I didn't know that. I knew that was the name of the road, but I didn't know that.
Did you go to MBA?
No, but I've gone to the beach like a million times. Their beach.
Having grown up there, I did too. Okay, here's our actual picture of the Ring of Fire. Can you see any plate boundaries in this picture? See this? What's inside the blue?
Ocean.
Which ocean? The peaceful one, the Pacific Ocean. So this is the Pacific plate here. This one here is the Nazca plate. And we have the South American, the African. This is the North American. And so we can see the plates. We can see strong rift zone right here, right? Woohoo! What's going on in Iceland? It's right on top of the rift zone, isn't it? It's got to be a volcanic island caused by the rift zone. And so you can see by looking at where we have volcanoes occurring, where the boundaries are for different plates. Which, once again, is very cool. Right, everybody?
Yeah.
Yes.
Okay. As long as you agree with me on that being cool, I'll be good to move on. What? It's fabulous. Just go quicker. What is going to cause the big one in California? Every time we have a little earthquake, we have two cracks that had developed strain that relieve the strain by sliding against each other. But if you think about it, okay, so we have two girls leaning against each other back to back. Let's say that there was a third person that was leaning, against, okay, Jocelyn's going to come be here.
All right.
Now, if I have Casey adjust a little bit to relieve some stress between her and Jocelyn, what's that going to do to the stress between her and Haight? I said Casey, right? What would that do to the stress between her and Casey if she moves a little to relieve some of the stress from Jocelyn?
Like a domino
It's
effect?
going to make it bigger. So every time you have a little earthquake, you build up more stress on the other faults until the stress gets so large on your major fault, the San Andreas fault, that it slides against it and you have big motion. And so you have a lot of energy that's released. And we had this nicely dramatized by our three actresses here. Thank you, young ladies. We appreciate the break from my talking. So how do we measure earthquakes? First, when I was a kid, it was with the Richter scale, and it's not anymore. Every now and then you'll have somebody say, it measured 6.2 on the Richter scale. But that's not what they report to you. Now, the Richter scale is a real device, and the Richter scale, basically you have a mass held by springs, and when the earth shakes, that mass, because of its inertia, doesn't. And so the Richter scale has a needle that moves back and forth to tell you how much that mass compared to or with respect to the earth moves, since the earth moved and the mass really didn't. And so the Richter scale measures how much motion there was in the earthquake. And the motion is important. Now remember, we talked about different types of waves. You have the S waves, the P waves, the Love waves, and the Rayleigh waves. And so there are different motions in different directions. So the Richter scale records that. And then they take that information and they put it into the moment magnitude scale. And so these days, when they say the earthquake was a magnitude 6.2, it has a moment magnitude of 6.2, and that moment magnitude takes into account the energy and the destructive ability. Different frequencies have more or less destructive abilities. And it's a number that's telling you about how destructive it is. And so an earthquake that is 1 greater on the moment magnitude scale should be about 10 times more destructive. So, a 6 is reasonably destructive. A 7 is very destructive. An 8?
You did.
Yeah, well, I mean, the one they had in New Madrid was a little bit above 8. But, 10 they consider would be annihilation of everything. But if you go down, 6 is some destruction. 5 is, well, I felt it. 4 is, really, was there an earthquake? Anything below that? Yeah, not worth counting. And I will end with tsunamis. Tsunami is a Japanese word that means harbor wave. Now, I was in Japan doing research, and I was watching the Nagoya Basho, a sumo wrestling tournament in Nagoya. And also the announcer says, oh, we just had an earthquake. There are not yet any tsunami warnings. And that was, of course, the English language broadcaster, because my Japanese wasn't good enough to understand. And then he says, now, what is a tsunami? Is that like? And he says something completely different. And I was like, you're in Japan and you don't know what a tsunami is? Well, I found out later that they were told not to say that there was a tsunami or potential tsunami warnings over the air because they didn't want to cause panic. And so he was trying to cover for that by obfuscating what tsunami means. But what is it? What is a tsunami? What other word do you use to mean a tsunami? Giant wave.
Mass
Really?
Water is great. Water earthquake.
When I was a child, we called them tidal waves.
The word.
You guys don't know that word?
Yeah.
Oh, okay. Tidal waves is not a name we're supposed to use in science because it's not accurate. So let's talk about what these mean and what a tidal wave / tsunami is. A tidal wave, the reason we're not supposed to use it is that it implies some connection to the tides. And it has nothing whatsoever to do with the tides. So why would the harbor wave be any better? Because a tsunami results when you have an earthquake that raised the water. So you have water, yay deep, and all of a sudden, like with the one that happened in 2004 or so in Accra, the land went up, if I remember right, something like 10 meters. That's like 3 stories, if I'm remembering right. That's a big upward shift of the land. And all of the water moved with it. Well, if you lift the water 10 meters, what's the water going to do? It's going to come back down. And so it starts a wave going away from there. Now that wave is a deep water wave. I say deep water. In physics terminology, it's still a shallow water wave. Even though you're going through water that might be a mile deep, it's still what we call a shallow wave because its wavelength is more than twice the depth of the water. And as this wave goes through the ocean, it travels at very high speeds, and the water level might be this much different. So if you're out there in a boat and there's a tsunami coming toward you, if you're in the ocean somewhere out there away from shore, it's just this little thing. Do you worry about little waves like this in the ocean? No. But if it's a tsunami, you do. Because that tsunami, you have the water in front is basically still. The water on the other side is rushing water. And so when that tsunami hits you, even though the height difference is just like this, you're going to go from stationary to the water's moving really quickly in one direction. And so your boat's going to have a tendency to tip, or God forbid, break, because of that force of going from still to rapid motion for the hull. Well, that's all fine and good until it gets to shallow water. In shallow water, you have all this energy of the rushing water, and it's got to go somewhere. So as the water gets shallower, instead of having water all moving like this, it then starts converting that energy to potential energy, building up a wall of water. So you don't really see the tsunami until you get to shallow water, hence the term harbor wave. You see the tsunamis when you get to the harbor, you don't see them out in the deep water. And if you've ever watched video of a tsunami, the last tsunami that hit the United States didn't cause much damage at all. In the U.S., it obviously took out the Fukushima reactors completely. I saw a video of the water coming into Santa Cruz. And, it comes into the harbor and it's only like a foot high. And I'm like, foot high wave? No big deal. But once again, on the other side of that wave, all of the water's moving. And so it comes to a wooden pier, and the wooden pier just goes traveling with it. It just tears it apart. And it gets to the, Baptos River? And it just starts cruising up the river because you got to stop that water. So tsunamis are not simple things to mess with. Even if it's only a foot high, it still has all that water traveling. It's like a high current coming along. So that's where we will end today.